Right, so exact differential equations. When you look at differential equation, again, at the beginning, we talked about classify a differential equation using different categories. Okay. But after you classify the differential equation, let's say to the first order differential equations, and you have tried separations of variable or integrating factor, and it's not even working with those two techniques, you have to move on to classify it something else so that you can use a different technique to tackle the problem. So the learning objective of this lecture is to identify when a differential equation is exact. To be honest, I don't understand what it means to be exact, the word exact in this context. It's just that with this type of differential equations is considered to be exact differential equations. In a way, there is the conditions that you need to use to check if the differential equation is in fact exact. It's just that I don't understand the context of the word exact in this in this technique. But anyway, this is another technique that or procedure that allow you to solve the first order differential equations. And to get to exact differential equations, I want to go back to some of the definitions that we see in multivariable calculus. The first one is the level curves, right? So that is the intersections of the surface z equal to a two variable functions or function of two variables with a plane z equal to c. So when you see this picture, this is the paraboloid, right? The one in brownish. So that's the surface, which is called the paraboloid. In this case, you have this curves in blue right here. Right? So this is the intersections of a plane z equal to something with the surface. Right? All of this intersections is called level curves. Right? Altogether, they call level curves. Now, if you have this curve and you project that onto the xy plane, all of these curves combined together, all the collections of all of these curves on the xy plane is called contour lines or contour curves. So let me quickly note that this is contour lines or contour curves. Okay. So I have this picture in the middle. Sorry. So the picture in the middle here illustrates the level curves and also the contour lines. Now, if you look at this graph from the top down, right, so z is equal to 0, you basically just look at the xy plane. This is you're going to see in terms of the contour lines or contour curves. So all of this curves, again, called the contour curves or contour lines. So in reality, is you see all of this before, like even when you younger, when you go to hiking and you have the map of the hiking place, you see the contour lines or contour curves on the map. So I'm gonna open of a hiking map and share that with you to show you that you have seen the contour lines before already without knowing multivariable calculus. Okay, so this is the map of the Blue Hills area. Right? So this is where it's a good place to go hiking if you around this area. So try it. It's very close. So this is in Massachusetts. So this is Quincy right here. The area of Newton area here. So this is Blue Hill. So Newton here. So it's Blue Hill, and you see the one in brown. So all of this curve that you see right here with the number. Right? Those curves or those lines are the contour lines or the contour curves, right? So that they have the mountain, they have the hills, and they have a bunch of z-plane to have the intersection between the z-plane and the surface, and then they project all the level curves, which is the intersections, onto the xy plane, and that's how they plot the contour lines or give you the idea of the elevations of the area that you are hiking. So the number here, I think, is 400 feet, 450 feet, so on and so forth. When you read this map, another characteristic that you can see is that how close or how far apart the contour lines. It's going to tell you a lot. Here in the first picture, this is kind of the sideway of the mountain, so to give you some idea of how it's going to be. You have again a bunch of z-plane, and you put that with the surface, create some level curves, and then you project all the level curves onto the xy plane to create some contour lines or contour curves. Okay. Again, the characteristic of this contour line is that the contour lines are close together, implies that the surface is steep, right? And if the contour lines are far apart, it implies that the surface is flat. So again, when you read the hiking map, you know where you want to walk, right? If you want to do a little bit challenging hiking, then you want to go to the area where the contour lines are close together. Or if you're the beginner like me, you want to walk on a flat surface, then you want to look at the map where the area of the contour lines are far apart. So the idea of me bringing up level curves and contour lines again is that from the contour lines, when you take the derivative of the from the level curves, when you take the derivative, right, something nice come up, and it's gonna come up something called the differential equations. And from this type of differential equation, you can classify it in a different class so that you can use something called exact differential equations to solve the solutions. Okay, so if you consider the level curve of the form phi equal to x comma y equal to capital C. So here's a few things I want to mention. The surface is the function of is a function of two variables, right? Usually written as z equal to something. Right? So z equal to f of x comma y. So most of the time when you see the surface in multivariable calculus, this is what you see. It's here, I just use a slightly different notation because a textbook that I use as a reference for this type of lecture notes. You can change, instead of phi of xy, you can use f of xy, you can use capital K of xy. You can use whatever letter that fit you, right? It's just that it follow the textbook that I use for reference. Okay, it's nothing major. So the surface is written as z equal to f of x comma y. The level curve is that those are the intersection of the surface with a plane z equal to c. Okay, and therefore you have the form phi of x comma y equal to capital C. So capital C is just some constant that you're going to use. Now, starting from this equation, if you take the derivative on both sides of the equation with respect to x, what you're going to have. Remember, the function you are dealing with is the function of two variables. So when you take the derivative of the function with respect to x, okay, so the right-hand side is simple, right? The derivative of a constant is equal to 0, so you have that. But on the left-hand side, phi of x comma y is a function of two variables. So when you take the derivative, you have to apply a chain rule. So here's the derivative. So partial phi partial x times dx dx plus partial phi partial y times dy dy. Sorry, times dy dx. It just say that you take the derivative of the outside function, but the outside function is the function of two variables. Therefore, you have to apply partial derivative. Then you multiply with the derivative of the inside function. So the derivative of the inside function is here. But again, because you have a function of two variables, you have to add the derivatives together. Right? So this part, again, is the partial derivative of the outside function multiplied with the derivative of the inside function. Again, the inside function is y in this case. But because we take derivative with respect to x, this is what you have. But derivative of x with respect to x is 1, and therefore you have partial phi partial x plus partial phi partial y times dy dx is equal to 0. Okay. Now, partial phi partial x is the function, right? And partial phi partial y is also the functions. So what we do is that we let partial phi partial x to be a function called capital M of x comma y, and partial phi partial y is a function written as capital N of x comma y. Then instead of this type of equations, you have a differential equation of the form that is m of x comma y plus n of x comma y dy dx. This is equal to 0. All right. So the exact differential equation, for now, the exact differential equation we're going to see has to start with this type of differential equations. Right? So we call this potentially this is the exact differential equations. We're not sure if it is exact differential equations. There's a test that you need to follow in order to show that this differential equation is in fact exact. Okay, so you may see this type of differential equation or written in this way, or you can see that is written in this form, capital M of xy dx plus capital N of xy dy. So this new form you have is called the differential form of the differential equations. Okay, so let me box this up. So again, this is called the differential form. So this form here is a differential equation form. This right here is a differential form. So they are slightly different that way. Okay, the way you write dy dx. So this is not dy over dx. This is the derivative of y with respect to x. So usually I say dy dx. But the second equation here is written purely in the differential form. So one function multiplied with dx, another function multiplied with dy. Most of the times, n of x comma y is the one get attached to dy, and m of xy get attached to dx. We'll see more of this later, but that's just the different forms that you may want to consider to solve using the exact differential equation approach. All right. So how could you classify as a exact differential equation? So you need to know the definition of exactness in differential equations and the conditions so that you can use to classify the differential equation as exact differential equations. So the differential equation, so let me start with this, capital M of x comma y plus capital N of x comma y times dy dx. So this is written again in the differential equation form, or it's written in a differential form. Right, either one. Right, when you see something like this, it's said to be exact in a region R if of the xy plane if there exists a potential functions phi of xy such that partial phi partial x is equal to capital M of x comma y, and partial phi partial y equal to n of x comma y. Okay, for all x comma y in R. Geometrically, so we mark here the solution curves of an exact differential equations on the family of curves phi of x comma y equal to capital C, where capital C is a constant. Okay. So it makes sense, right? Because we derived this type of differential equation starting from level curves equations, starting from here. Therefore, if you have the differential equation of this form, then you can find the solution, and the solutions therefore has this equation. Okay. Now, how do you test the exactness? So let capital N, M, and N and their first partial derivative, capital M sub y and capital M sub x be continuous in a simply connected region R of the xy plane. All right, you may wonder what is simply connected region. So this is, we don't have time to go over all type of the regions, but simply connected regions in a way just is a very nice continuous way to look at the regions, right? So there's no holes inside the regions. It's very smooth, very nice area to work with. That's kind of the general explanation for the simply connected regions. All right, so we need this type of regions in order to test for the exactness. Therefore, all the functions, capital M and capital N that you're going to see in all the example that we're going to cover are very nice functions. Nice mean that they are continuous, they are differentiable functions. All right. if all of this function and their respective first partial derivatives be continuous in a simply connected domain or regions on the xy plane, then the differential equations of xy plus nxy dy dx equal to 0, or xy dx plus nxy dy equal to 0 is exact for x, or x and y in R, if and only if partial m partial x equal to partial n partial y. All right. So this is the conditions that you need to use to check if the differential equation is in fact exact differential equations. So you need to look at the differential equations, pick out the functions capital M of xy and capital N of xy. Find partial derivative of m with respect to x, find partial derivative of n with respect to y. If you get the same thing, then you can classify the differential equation as exact differential equation. So this is, can you go back here and fix this for me, please? So partial m partial y equal to partial n partial x. So sorry about that. So equation 1 is an exact differential equation if you have partial m partial y equal to partial n partial x. Or a slightly different notation is that m sub y equal to n sub x. So just the partial derivative. Now, after checking that differential equation you work with is exact differential equations, you start finding the solutions. So suppose there exists a function, let's call the function phi of xy, such that partial phi partial x is equal to capital M of xy, and partial phi partial y equal to n of x comma y. So again, this procedure is kind of the reverse process of what we see earlier, starting from the level curves down to the differential equations. Now we just go in the reverse direction, starting with the differential equations. Can you get to the solution as level curves? Okay. So this is where partial phi partial x coming from and partial phi partial y coming from. Okay. Then instead of this type of differential equations, you have that instead of mxy plus nxy dy dx, what you have is this one is partial phi partial x, and this is partial phi partial y. Okay. This implies that you have partial phi partial x plus partial phi partial y times dy dx. Okay. And from here, remember that the left-hand side is written as is actually from the derivative of phi of x comma y, and then we use a chain rule to arrive at this expressions. Right. So this can be written as d dx of phi of x comma y equal to 0. So this implies that when you take the derivative of a function is equal to 0, then the function is a constant, right? Equal to a constant. So this implies that phi of x comma y is equal to a constant, and I call it constant capital C, where C is just an arbitrary constant. Okay. So we just know that phi of x comma y is equal to a constant due to these equations. Okay, but we didn't get the chance to show the representations of phi of xy, right? Because of the contour lines or the level curves. That phi of xy is the function of two variable x and y that equal to a constant. So here's what you can do. Starting out with either this equation or this equation. So I call equation 2. This is 3. I'm going to start out with equation 2. So from 2, I have that I'm going to take antiderivative or integral of integrate both sides of these equations. From 2, I get phi of x comma y equal to the integral of m in terms of x. When you find the integral of m, you have an antiderivative of the form capital F of xy plus some constant. Okay. Remember, we are working with function of two variables. Right? So when you take antiderivative or find the indefinite integral, you have not only the antiderivative, but usually the plus c at the end, right? An arbitrary constant. But in the context of the function of two variables, in this case, you integrate with respect to x. Therefore, the constant can be arbitrary constant, but also the letter y, right? Something related to y, because in this context, y is a constant. Okay, so instead of just some arbitrary constant, I just put in a function in terms of y, because in this context, h of y is a constant. And this is the general solutions. Now you get the representation of phi of xy in terms of f of xy plus h of y. Now the next step is to find the representation of hy. Right? And we do that by using the third equation here, or equation number 3. That is partial derivative of phi with respect to y. We take the derivative of the phi with respect to y and match with capital N of x. So from here, you take partial derivative of phi with respect to y and match with these equations. So partial phi, partial y. So partial derivative of f, capital F with respect to y, plus the regular derivative of h of y. And this is set to equal n of x comma y. And from here, you can find the representations of x prime of y, which is used to find h of y. So let's consider the following example. So consider the initial value problem. You have the differential equation of the form 2xy minus 9x squared plus 2y plus x squared plus 1 times dy dx equal to 0. And this is the initial conditions. And they ask you to check that the differential equation is in fact exactive equations. Then find general and particular solutions to the initial value problem. Okay. So you need to find capital M of xy and capital N of xy. So this is capital M of xy, and this is capital N of xy. So N of xy usually get attached to dy dx. So find partial M, partial y. So that is, so this is the first problem. Let me do this slowly. So partial y of 2xy minus 9x squared. So you take partial derivative with respect to y. X in this case is a constant. So partial derivative of y is 1. With respect to y is 1. So you just have 2x. Partial derivative of this term with respect to y. So there's no y, so this is 0. You get 2x for the answer. Now, you do partial n, partial x. That is, you take partial derivative of 2y plus x squared plus 1 with respect to x. So partial derivative of 2y with respect to x is 0. There's no x term in there. Partial derivative of x squared with respect to x is 2x. And partial derivative of 1 is 0. So this is 2x. So we say that since partial m, partial y equal to partial n, partial x, right, we say that the differential equation is in fact exact. So that's how you check if the differential equation of consideration is an exact differential equation. Okay. Now we know that it is a exact equation, then we're gonna follow the procedure that we see earlier to find the general solution and eventually the particular solution of this initial value problem. The procedure is very repetitive, right? So if you follow this structure, you should be able to arrive at the answer. So suppose there exists a function, and I call this function phi of x comma y, such that partial phi, partial x is equal to capital X of y, in this case, capital X of y, sorry, m of x of y, capital Mx comma y is equal to 2xy minus 9x squared, and partial phi partial y is equal to capital N of x comma y. This is equal to 2y plus x squared plus 1. Now, suppose there exist as such functions. Then, from the first equations, partial phi partial x equal to 2xy minus 9x squared, you integrate both sides with respect to x. And you get phi of x comma y equal to the integral of 2xy minus 9x squared dx. Okay. So that's how you find the integral. Now you integrate each term in the integrand. So the integral of x is x squared over 2. The number of y in this context is constant. So antiderivative of x is 1/2 x squared. So you have 2 times 1/2 x squared times y minus 9 times 1/3 x cubed. Right. So again, the antiderivative or the integral of x squared is x cubed over 3 or 1/3 x cubed. Plus a constancy, usually because we are working with indefinite integral, but here we have a plus constant, and the constant representation is h of y. Okay. So we have a form of phi of x comma y, but in that form, there is still something that missing that we still need to find the representation for. That is h of y. Okay, so let me simplify the equation a little bit. That is x squared y minus 3x cubed plus h of y. So you need to find the representation of h of y, and we can do that using this second equations right here. Okay. So to find h of y, we take partial derivative of phi of x comma y with respect to y. Then, so partial phi partial y, take partial derivative of this. You have x squared minus 0 plus h prime of y. So partial derivative of this term with respect to y can give you x squared. Partial derivative of this terms with respect to y, there's no y terms here, so this is 0. And partial derivative here is the function in terms of y only, so we come up with the regular derivative. Yeah. So let's take a look at these two functions or equation. So these two equation. Okay. They are both partial phi partial y. Right? So the left-hand side of the two equations are partial phi partial y, so you can set them equal to one another. Set the two equations in the box equal to one another. We get that x squared plus h prime of y equal to 2y plus x squared plus 1. So now you can find h prime of y, and from h prime of y you can integrate to find h of y. So you cancel out the x squared on both sides of the equations, and you left with h prime of y equal to 2y plus 1. You integrate both sides with respect to y, you get the integral of 2y plus 1 dy, or this is y squared plus y. Now you can do a plus constant k. Okay. So I reserve the constant c for later. So you have h of y. Now you go back and say that then phi of x comma y is equal to x squared y minus 3x cubed plus h of y. So in this case, h of y is equal to this equation, so equal to this expressions. That is y squared plus y plus k. But remember, the solutions we're looking for is level curve solutions. In addition, phi of x comma y is equal to c, but in this case, let me call that c1. And then combined together, you have x squared y minus 3x cubed plus y squared plus y plus k equal to c1. So this is the solutions you're looking for. So this is the general solutions, and of course you can simplify this type of equations even further when you combine the constants together. So k is a constant, c1 is the constant, you combine them together and you get the solutions of the form that is x squared y minus 3x cubed plus y squared plus y equal to some constant c only. So this is the functions that you're looking for. So this is the general solutions written in the implicit form. General solution in an implicit form. The next step is to utilize the initial conditions to find the value of capital C. And when you get capital C, then you have a particular solutions. So let me fix this one real quick. So implicit form. So the initial condition is y of 0 equal to -3. So given y of 0 equal to -3, we get that. So x equal to 0, y equal to -3. We get 0 squared times -3 minus 3 times 0 cubed plus -3 squared plus -3 equal to constant c. And if we do the calculations correctly, you get c equal to 6. Thus, the particular solutions is x squared y minus 3x cubed plus y squared plus y equal to 6. Right, so that is the particular solution. Now I want to present to you the solution curve on another tool. This is called GeoGebra. So I don't know if you have used something like that before, but I think it's a very powerful tool to visualize the function of two variables. So give me 1 second here. So the equations that we got, it's x squared y minus 3x cubed plus y squared plus y equal to 6. So let me start with the constants equal to 6. And you have x squared times y minus 3 times x cubed plus y squared plus y equal to c. So that's the solution curves. Okay. So in case that you have to, not only this particular solutions, but you have just the general solutions, you can animate this type of curves to visualize the solutions better. So see if I can visualize, animate this. I was able to animate it yesterday, but okay. So initially, this is what you got. All right. So this is the initial curve. So if you have a the particular solution curve, if you have a different initial value, so initial conditions, then you will have a different curves out of this. So you can animate and you can see a different shape to the solution curve. You can visualize that way. Okay, so good. Move on to example 2. Again, you're going to find the solutions to this initial value problem. You have a differential equation, you have the initial conditions. The first step is to check if the differential equation is in fact exact. You're going to pick out the functions capital M of xy and capital N of xy. So in this case, capital M of xy is equal to y times cosine of x plus 2x times e to the y. And capital N of xy is equal to sine of x plus x squared times e to the y minus 1. From here, you find partial derivative of y with respect, partial derivative of m with respect to y, and partial derivative of n with respect to x. So you have partial m, partial y is equal to, so partial derivative of this term with respect to y, it's just cosine of x, plus partial derivative of 2x times e to the y. So partial derivative with respect to y is just e to the y in this case, or 2x times e to the y. Similarly, you're going to do partial n partial x, and you get partial derivative of sine of x with respect to x to give you cosine of x. Partial derivative of x squared is 2x, so plus 2x times e to the y. So partial derivative of -1 is just 0. So partial n partial y equal to partial n partial x. So this implies that the differential equation is exact. Okay. And then you follow the procedure to find the general solutions of the differential equations, then use the initial conditions to find the particular solutions. So suppose there exists a function phi of x comma y such that partial phi partial x is equal to capital M of xy, or this y times cosine of x plus 2x times e to the y, and partial phi partial y equal to capital N of xy equal to sine of x plus x squared times e to the y minus 1. So you have two equations. Again, you can start with either of these equations to find the representations of phi of x comma y. I'm going to start with the first equations. So you integrate this equation, let's say equation 1, and this is equation 2. All right. So you integrate both sides of 1 with respect to x. We get that phi of x comma y equal to the integral of y of cosine of x plus 2x times e to the y dx. So antiderivative of cosine of x with respect to x is sine of x. Remember, y in this context is a constant. So you have y times sine of x plus the antiderivative of e to the y is just e to the y. Sorry, the antiderivative of x is x squared over 2. We're doing this with respect to x. So you have 2 times 1/2 x squared times e to the y. And then, of course, at the end, we are dealing with the indefinite integral, so you have plus c, but again, in this context, it's going to be h of y. And we're going to use second equation here to find the representation of h of y. So simplifying this function a little bit, so phi of xy is y times sine of x plus x squared times e to the y plus h of y. So to utilize number 2 or equation 2, what you do now is from this equation, you take partial derivative on both sides of this equation with respect to y. Whatever you got, you match with the right-hand side of equation 2. Okay. That is, you take partial derivative of phi with respect to y. That is, partial derivative of this terms with respect to y is just sine of x. Partial derivative of this terms is x squared times e to the y. Then partial derivative of h of y, because this is the function in terms of y only, so it's just a regular derivative. And you set that equal to the right-hand side of equation 2. You get sine of x plus x squared times e to the y minus 1. And from this equation, it's allow you to find the representations of h of y. So first, cancel out sine of x on both sides of the equations. Cancel out x squared times e to the y on both sides of the equations, and you're left with just x prime of y equal to -1. Then integrate both sides of the equation with respect to y. You have h of y equal to the integral of -1 dy, which is -y plus a constant. In this case, let me use constant c1. Then we obtain the representations of phi of xy. So phi of xy is, from here, is equal to y times sine of x plus x squared times e to the y plus h of y, given that h of y is equal to negative y plus c1. And remember, again, the solution has to be in terms of the level curves. Right? So when you're looking for level curve solutions, so set this equal to capital K. Right? Again, C1 is a constant, K is a constant. Now you combine them together to have another constant. Therefore, the solutions, the general solution is y times psi of x plus x squared e to the y minus y equal to a constant c. Again, c is the combination between c1 and k. Now that's the general solution. So we're going to use the initial conditions to find the value of capital C. When you do that, you get the particular solutions. So the initial condition in this case is y of 0 equal to 0. So given y of 0 equal to 0, that means that x equal to 0, then y equal to 0. We get that 0 times psi of 0 plus 0 squared times e to the 0 minus 0 equal to c. This implies that constant c is equal to 0. Then the particular solutions is so you have y times psi of x plus x squared times e to the y minus y equal to 0. So this is the particular solutions that we're looking for. So let me again plot these curves on in GeoGebra and then the website that we use to visualize direction field and the solution curve and see what we get. So solutions that we have is y times psi of x plus x squared times e to the y minus y equal to a constant, right? So in this case, the constant is equal to 0. So that's the solutions, the particular solutions that we're looking for. Of course, you can animate this to see how for different initial conditions, the shape of the functions look like. Right? Something weird, so something like that. Let me zoom out a little bit. Oh, this is interesting. Okay, so that's the solution curves. So example 3, check that the differential equation is in fact exact equations. So capital M of x, y is equal to 2xy plus 1/2 y squared. So partial m partial y is equal to 2x plus y. So I'm going to split up a little bit because as you see, they are very repetitive. It's just you need to follow the procedure closely and be careful with the calculations. Okay. Now capital N of x comma y is equal to x squared plus xy, implies that partial n partial x give us 2x plus y. So since partial m partial y equal to partial n partial x, the differential equations is exact. So DE means differential equations. Now we know that this is an exact differential equations. We're going to follow the procedure to find the general solutions, then utilize the initial conditions to find particular solutions. So suppose then there exists a function phi of x comma y such that partial phi partial x is equal to m of x comma y. In this case, it is equal to 2xy plus 1/2 y squared. And then partial phi partial y equal to capital N of xy is equal to x squared plus xy. Okay, so very similar to last time, I'm going to name this equation 1 and equation 2. And from equation 1, to find the representations of phi of xy, you integrate both sides of the equations with respect to x. So from 1, we integrate both sides of the equations with respect to x. We get that phi of x comma y equal to the integral of 2xy plus 1/2 y squared dx. So in this context, y is a constant. All right, so antiderivative of x is 1/2 x squared. So you have 2 times 1/2 x squared times y plus 1/2 x times y squared plus h of y. Again, in the definite integral, you need to have a plus arbitrary constant, but y in this context is a constant, so that's why we use h of y. Simplify the equation a little bit, you get b of x comma y equal to x squared y plus 1/2 x times y squared plus h of y. Now, we still need to find h of y. We can do that using the second equation or equation 2. Now, to use equation 2, what you do for the next step is take partial derivative on both sides of these equations with respect to y. We got partial phi partial y equal to x squared plus xy plus h prime y, and set this equal to the right-hand side of the equations. Number 2 here, that is x squared plus xy. Then you simplify this, cancel out this, cancel this out, cancel this out, and you're left with h prime of y equal to 0. When you have a derivative equal to 0, that is the antiderivative is just a constant. So h of y is equal to some constant k. Let's say constant c1, sorry. Now the representations of phi of x comma y is equal to x squared y plus 1/2 xy squared plus c1, and you have to set this equal to a constant because you are looking for level curve solutions. And the general solutions is that is x squared y plus 1/2 xy squared equal to a constant c. Again, c is an arbitrary constant, and it's the combinations between c1 and capital K. Now we're going to use initial conditions to find the particular solution. So the initial condition in this case is y of 1 equal to 0. So x equal to 1, y equal to 0. So given y of 1 equal to 0, we got that 1 squared times 0 plus 1/2 times 1 times 0 squared equal to c, or c is equal to 0. So in this case, the particular solution is, so the particular solutions is x squared y plus 1/2 xy squared equal to 0. And that's it for the exact differential equation lecture. So in this lecture, we go over another solution technique to find the solution to the first order differential equations. The differential equations in this case is, of course, linear differential equations. So you'd be able to classify linear differential equations in the first order differential equations. And the differential equation is usually written in this form, that m plus n times dy dx, or m times dx plus n times dy equals to 0. And this is potentially the exact differential equations. Potentially means that you need to check if this is in fact an exact differential equations. Okay, and the differential equation is exact if you have partial m, partial y equal to partial n, partial x. Okay, so usually when you encounter this type of differential equation, that's the first thing that you need to do. Identify n, find partial m, partial y, and partial n, partial x. If they are equal, then you can conclude that the differential equation is exact differential equations. Then you follow the procedure to find these solutions, and the solution has to be in a level curve form. Why level curve form? Because the differential equation is actually derived from the level curve or the control lines form. Okay, so that's it for me of lecture 6.